Assalamu alaikum everyone. Ready inshallah for 8th lecture of the course. Last time some of you were sleeping, okay, the majority, and you did not prepare. So today inshallah we're gonna have a very powerful technique, yet very, very simple. So actually the idea of today's lecture is extremely simple. And the implementation with Keras and Tensorflow, as we're going to see inshallah later, it's really straightforward, but yet it's very powerful, and a lot of people are using it. So let's first start with a recap, as usual, with what we've been covering before. So lecture 5, so it was 3 lectures ago, we trained fully connected neural networks, which are also called feed-forward neural networks, FNNs. And there's also another name for them. They're also called vanilla neural networks. So if you ever hear this name, so this is the kind of neural networks that's meant. And we trained them on a set of characters, the MNIST dataset, and we saw the performance, and we played around with it a little bit. I played around with it a bit. You didn't yet. Okay, so you're gonna do it inshallah for assignment number 2, homework number 2. Yeah. And in the previous lecture, we looked at convolutional neural networks. And the idea behind convolutions is that we add more structure into the networks. We don't take them pixel by pixel. We do this convolution operation such that we can learn, we know that we're training for images. We know that the data set is images. So we say, okay, let's do this convolution with some kernels with unknown parameters. So we don't design the filters. We let the network train it itself to learn these filter parameters, these kernels. And we saw that, okay, you just stack a number of these, and then in order to boost the performance, you need to use some regularization techniques, like, for example, what we discussed, the dropout, batch normalization. We discussed data augmentation to increase the data set. And there was also this idea of early stopping and using some of the data set for validation. We're gonna see some of these regularization techniques again today, inshallah. And okay, and this is and if you remember from last time, the idea was also that the convolution part, or the convolution layers that we add, they do some sort of feature extraction. So they're learning the hidden features that are within the images, and then in the end we connect this to a normal fully connected network that's taking care of the classification. Okay. What is transfer learning? So the topic of today in a nutshell, and you've seen last time that we've been training the convolution neural networks. They took some time and we reached not very good accuracy. So, and you've started to see with this CIE483 data set that it's really difficult to train neural networks, especially if you have limited data and limited compute power. So 3 levels. So at one point, you can have just very few data sets. Is this the case for images? Yeah, no, because if you're talking about images of standard stuff like cats and dogs, the web is full of them. If you're talking, for example, in the medical section, in the medical field, and if you're talking about images, for example, of MRI by data, okay, maybe they are not as much as cats and dogs. Okay, maybe they're harder to learn, so maybe that's one point. MRI is this magnetic resonance device where you go, God forbid, if you want to, for example, look at within your body, something like that. What? Yeah, exactly. It's something with magnetic resonation. Okay. If you have a robotic data set, so let's say if you have a data set of robot, and this robot you want to classify nails, for example. Okay, so let's say that you have a robot arm and then you want to have a classification of nails. How many images do you have of nails? Is there a data set of nails that exists? So all of these are questions. Let's say that this is your problem. You want to design a robot for this problem. You might not have enough data, right? So the data on the of cats and dogs, and like, for example, ImageNet, yeah, it's been built with a lot of effort. And remember, to train neural networks, you don't only need the images. What else do you need? Yeah. The labels, which is even more difficult. And labeling the data set is a very tedious job. Okay. and it was very expensive. Another point, let's say that you have the data. Is it easy to find compute power? Okay, this is this is very tricky. Okay, now the next war that will happen is happening over this kind of devices, right? So the ship wars. Okay, if you see what's going on between China and the US and Taiwan, it's all in this area, because really having the processing power, okay, is very expensive, and yeah, it's very rare. Especially if you have really the hard, very hard problems. So last time, if you remember from this table that you see here, that that in order to boost the accuracy to go above 95% on the test data set, we need to have a lot of parameters. So we need to have very either many convolution layers or very deep networks in that sense. And you see, this training time is actually using GPUs. Okay, don't even imagine if you only have a CPU how much time this would take. Okay, so and again, this was with one type of GPU. So this was just a case study that's available on the internet. If you have more powerful computers, you can do it in less time. But if you can imagine how this scales up with a lot of parameters. Even if sorry.
Does the label of the data set usually done manually or?
It is manual, yeah, of course. It's part of building the data set.
Have a lot of very large data set.
This, students are very good for that. So if it's done within within a university, these are being labeled by students or by employees that just take money to CAD doc, and so on. Okay. Or maybe there are smarter ways to do it again, but it has to be done. You have to provide it with the data set. And even if you have the good compute power and you have the limited data, you might take weeks, you might take months to train very complicated neural networks, which is part of the difficulty of the limited compute power. So the idea of transfer learning is the following. People have already spent like considerable amount of time in pre-training these models. Some of them already shared their models with people so that they can use this model. So the idea is, why don't you use this pre-trained model, okay, instead of designing one yourself? So instead of designing a neural network from scratch, instead of using a neural network from scratch, why don't you use the pre-trained model? But the pre-trained model might have more than what you need. So, and if the pre-trained model is done using convolution neural networks, the first layers in this network would extract the features in images in general. So why don't we use only the first layers of this network? And let's recall this idea of the feature maps. If you remember, this is something very similar to what we were doing last time, not exactly, but something similar. So last time, if you remember, we had the Cipher10 dataset. So we had an output, we had 10 labels that we want to classify images in. And we had a number of, this was not precisely the network that we were using, but it's something similar. So we had convolution, activation, and then we did pooling, convolution, activation, and then pooling, and so on. And then to regularize, we added some dropout and batch normalization layers. But in the end, after that, we flattened the image, we flattened the layers, we connected to a fully connected network. And then we have the softmax activation just to give a probability for all of these, probability of what this image is. So this first part is very interesting, and it's usually the most difficult part, right? And if you remember from last time, you can do it in two ways. You can either do the fixed feature extraction by hand and do the classification separately. And this is what people are doing in machine learning. Other methods other than deep learning. But when we talk about deep learning, we do the learning to the feature extraction and also to the classification, both at once. So this is what we did from last lecture.
So the deep learning, initial steps, in the neurons directly, right?
You mean with the convolution neural network?
Extraction here, for example, the first several steps, feature maps.
Yes.
Then deep learning directly go to the neurons, or we have to extract the features and then go to the neurons.
You mean the neurons of the fully connected nerve? So so the question was, when we use these filters, how are they connected to the fully connected network, right?
Yes, I mean, is it separate or directly, automatically done in the neurons?
So the last layer, the last operation of after the last layers of convolution, this is what we connect directly to the fully connected neural network by the flattening operation. But what we're doing before, they are also kind of neurons, by the way, because the weights of the filters, we are also learning them. Okay, but by knowing that these are actually that they have they are 2D arrays. So we put more structure. So we learn much fewer parameters than what you would have needed if you would have a fully connected network from the images to the labels.
So the image like input neurons, you can consider doing like this stuff.
The convolution doesn't, if you consider them as pixels like what we did in lecture 5, okay, then you consider each pixel as a neuron, okay, as the input layer. But now when we take the input to be the image and we do convolution, okay, we get also as output images, other images. So that's why you see them, they're also, the output of each convolution and activation and pooling was also a 2D map. And they are also images. And by the way, if you look at them, it's something we didn't do last time, but if there are some techniques that you can hack into, not hackers, you need to use some low-level APIs from TensorFlow, not Keras this way. And you can look also at the layers. What is the output of the layers? Because they are images. So you can look at the images. And if you do that, this is a very nice paper. It's a very famous paper that actually shows you shows the inner workings of convolutional neural networks. And you see that the low-level features, they learn abstract, okay, features. When you go to the middle level features, they get more, okay, into something that we can associate. When you go to the top level features, this is you start really learning about objects. For example, if you look on this image in the lower row, you see that it's starting to learn something like a beak of a bird. And if you go to the top one, for example, you start to see that it's starting to create objects like wheels or something that are available, or something in the circular, like what happens with the jet of an airplane, and so on. So for the top level features, it starts to learn objects, okay, that you might see in this image. But for the low level features, of course, for us, they're not understandable. But they might be a combination of, for example, like features, or like abstract circles, abstract corners, and so on, okay? So for us in the transfer learning, the idea is, if there was a pre-trained model, it would have very good classification, it would have been trained on to produce very powerful low-level features that would take us a lot of time to produce. Okay? So the idea is, why don't we use these features, these low-level features, and maybe the middle-level features, okay, and maybe some of the top-level features, but then instead of having them classify the cars, have them classify, for example, what we're interested in. Okay.
So this is the pre-trained model has been trained with a different data set.
Yes, exactly. But that's the point. That's exactly the point. These features are, of course, they come from the same data set. So okay, that's a very good point. So the pre-trained model. Okay, why don't I answer this in the end? Okay, when I just finish the idea of the neural transfer. I'll come to that point. It's a very, very, very powerful point. So this is the idea of the idea of the transfer learning. Very simple. So if you have a model like any one of the you have very powerful models that we didn't even discuss, that have been trained on ImageNet. If you go to I think to the first lecture we talked about deep learning, there was this table on the ImageNet and some of the graph. There was the graph of the top 5% error of some networks. So again, if you choose one of these networks created by Google or Facebook, and top players in the world are competing in this, you'll find that for you, the feature extraction part and the classifier part is both trained. Okay, so if you download it and you run it on the ImageNet, it will do the classification for you. This is something that you can do actually. You can just download this parameter. This is a program, remember. Okay, you give it an image and it will give you a classification. So this is something you can download and you can make use of. And this is classifying now 1,000 classes. So you can imagine how complicated this is. Let's say that you're interested only in cats and dogs. So you only want to train cats and dogs. And let's assume that the cats and dogs were not available in this data set, okay? So let's assume that ImageNet was not trained on cats and dogs. Or you have specific cats and dogs. Let's say that you have your cat at home and your dog at home, and you want to classify only these two, okay, objects. Okay, so of course your cat and your dog were not in the ImageNet data set, but there were cats and dogs. So yeah, it knows how to classify cats and dogs, but maybe not your special ones. So the idea is, if you were designing a neural network, what you would have to do is that you would have to train, you would start from an untrained feature extraction, an untrained classifier, and you would have to run the whole, you would have first to have many pictures to a large data set. You need to have thousands of images of these two classes. You need to label them, you need to give them to the neural network, and then you need to train, and then test whether this is a good accuracy. But what we did last time. This is transfer learning. Let's take the feature extraction from the trained models, and let's add our own classifier part, our own classifier labels on top of that. And then let's train this part alone. Okay. So we're going to train the network only the last layers that we added, the ones that are responsible for the classification, okay? Which are these parts. So the fully connected layers. This is the one responsible for the classification.
So we will give it, for example, 10 classes.
In this example, it's only 2 classes. So you're only interested in 2 classes. So labeling two types of images is much easier. Labeling 1,000, okay? And you have also few data sets. So this also works if you have like in the range of 1,000 images or something, okay?
So the feature extractor on car, for example.
Yes. Yes. ImageNet.
But how, when you give the class, for example, capital, how it's going to expect this?
So again, the feature extraction, again, so if you look at here, so remember what the classification does. The classification will associate these top level features to the cats and the dogs, right? So maybe a cat has like 1% of this, 2% of that, 5% of this, so plus 6% of that. So this is the weight, right? You combine these images, you add them, and you get a cat. This is the idea of the classification. So these are features. What's inside of the neural networks is not parts of cats and dogs. Okay, we hope so, right? And this is why these kind of neural networks are black box. We don't know what is going on inside. Okay, we can see some images, but it's very hard for us to explain it. Okay, we can't know. It has some intelligence, so it is an intelligent agent, but it's not different intelligence from the one that we have. Okay, and that's why we cannot explain what's inside, even if we look at it and see. But still, you can associate some classification to these features to cats and dogs. Okay, this is the idea. Okay, ImageNet was trained on much more than cars. You might think of, okay, if I have a network that was trained on cars, can I use it for cats and dogs? Probably not. And this comes to your question, right? You have to have transfer learning only works in one scenario. When the probability distribution of the small data set that you want to work on is included in the big data set. So this is the condition, okay? So you have to have that they are very similar distributions.
So we will implement transfer learning. We jump to the test data. Training.
You do some training. You do something. We're gonna see it, okay? And this is actually the part. So what you do. So there are two ways of implementing this, okay? And usually you do both of them to implement transfer learning. And the first one that you see, so the first line that you see on the left, okay? So this is the left of the screen, okay? Yeah, okay, the left. Why is this? Yeah, okay, it's on your left, okay? On your left. So the input goes through 1, 2, 3, 4, 5, 6 layers before then it's mapped to the output label. What you do is first, you download the pre-trained model, you download all 6 layers with the weights that come with them. Okay? That's you can do. And then what you do is that you freeze the first layers, the early layers in the networks, the one that are responsible for the feature extraction, you freeze them. and you only train the last layer, okay, or the last layers again of the classification
of the neuron.
of the neural network, of the fully connected neural network. Exactly. Okay. Yeah.
No, you mean that you bring a neural network from the internet
Yes.
and you freeze the first
Layers. Yes.
and then train the rest.
Exactly.
So for avoiding what?
For doing a transfer learning. Because when you do that, okay, you're going to be training. Okay, the question is, what are you going to be training this freeze network on? You're going to be training it on your data set. So the full network was trained on ImageNet.
And another classification problem, right?
And another classification problem. Okay, that is similar. That has similar distribution than the one that's okay. That both have to be similar. They have to have the same probability distribution. Okay, this is very important. So if it's cats, if the image, if the original data set was cats and dogs and trees and deers and frogs and so on, and you want to train only on cats and dogs, this can work. If the original data set was trucks and cars and airplanes and ships and so on, I don't know. Something to play around with. Does it work or not? I don't know. Okay.
So your class must be in the previous.
It's not really this much because remember, as images, they're completely different. So again, we have to think of in terms of a probability distribution. It's an easy way to describe when transfer learning is to characterize this data set has the same probability distribution as the other one is a little bit tricky. Okay, there are some mathematical ways to do it, but it becomes very involved.
To provide the probability distribution, you mean similar features on each image?
That's exactly what I'm saying. It's tricky to characterize. Okay, it's tricky, but again, from a probability distribution point of view, they have to be similar. This is the idea. This is just the intuition. Okay, clear? So the first step you do in transfer learning is that you remove the layers, okay, and you put your own layers in the end. Okay, so these green ones are your classification layers that you put. They're untrained, and you train the network for these ones. And even in the end, you can do something. So let's say that this will give you like 90% accuracy, okay, if it works, and you want to boost a little bit the performance. What you can do is that you can then do something called fine-tuning, which is very simply unfreeze the previous layers, okay, which means you're going to be learning much more parameters on the small data set that you have, but do it with a very low learning rate, okay? And the very low learning rate, what it will do, when you have a high learning rate, what does the gradient descent algorithm do? If you imagine that in 2D, you have the parameter space, you're looking for the theta, and you have a high learning rate, what does the high learning rate do? That's very, from step to step, does a very big jump, exactly. If you have a low learning rate, what does it do? Very small jump. Okay. So although you're looking in a huge parameter space, because now you're looking in the parameter space of the whole network, you're going to be taking very, very small, tiny steps. So this is called the fine tune. Okay. Okay. Very small, tiny steps. Clear? That's it. This is transfer learning. Okay. It's very simple, but very powerful. And by the way, a lot of people that really produce a lot of results make use of that. Okay, they stand literally on the shoulder of giants. Okay, they take pre-trained networks, play around with them, and make them work for their algorithms. Okay, and they make a lot of money out of it. Okay, if you
the thing is the probability distribution.
Exactly, but then yeah, they can play around. Again, this is one way that you can crunch numbers, put in a lot of tries, different stuff, try different networks, see what works, and again, within a week, instead of spending the whole week on training one neural network and you don't know whether to work or not, you can spend this 1 week on trying different models, right, and training very fast for your own data sets. It's a very strong power mindset, and it gives you a lot of good results. And we're going to see right now, actually. Okay, so let's go to the code and start implementing this. Okay. Let's go. Okay. As usual, the tutorial is also well documented. I didn't write it myself. Actually, most of the other tutorials I didn't write myself. I just modify a little bit and used from other resources I usually mention in the beginning. This one is really based on a very nice tutorial. That's even part actually of the Keras library. Okay, so this is yes, of course I can zoom in. So let's remove this part. We don't need this one, and let's go. Is this good enough?
Yeah.
Okay. So let's see. Import some stuff. Okay, let's see, working with GPU, perfect. And I already described what the idea of the transfer learning is. You have it here also mentioned again. And Keras gives you something very nice. That's this idea of freezing and unfreezing layers, right? It's already implemented in Keras. You just have to use the API for that. And I'm going to show you here something about something that was actually included in the previous lectures. You probably saw it, but maybe you didn't comment on it. And it's this idea of trainable weights and untrainable weights. Okay, let's build a very simple network that has 4 neurons as input and an output layer of 3 layers. Okay, 4 neurons input, 3 neurons output. Okay, so the weights. Okay, you have what? No hidden layer. Just an input output map. Very simple. Just to demonstrate this idea of the trainable and untrainable weights. You see, now we build the layer, okay? And then there is an attribute called layer.weights, another attribute called layer.trainable weights, and layer.non-trainable weights. If you print these for this very small network that we have, you see that we have 2 types of weights. So this is not the number of weights. This is just the 2 types of weights. And these 2 types are simply the weight matrix and the bias, okay, of this fully connected network. And out of these 2 weights, you have 2 of them trainable and 0 non-trainable. Okay. The trainable means that the numbers inside of this array, actually the first one is a 4x3 matrix and the other one is a 3x1 matrix, right? Because we had, if you remember, this was W multiplied by the input plus B, okay, and this gives the output. So because you have, sorry, it's a 3x4 matrix. Sorry, 3x4. Again, this the way that Keras implements the weights is up to them. That they decide how they want to organize the dimensions. Okay, but for us, it's the weight is a 3x4 matrix. Okay, we have 12. In both cases, we have 12, right? But again, we think of them as 4x3 matrix. Sorry, 3x4 matrix because the input is 4 and the output is 3. This is the case. So you see here. No, it's a W multiplied by the input plus the parameter plus the input. So it's a different way. You see here, so this is weights. So the weights is an array that has 2. So one is the 3x4 matrix, and the other one is the 3x1 vector. Okay, this is how it's organized inside of Keras. But the point I'm trying to make here is that you see that you have trainable weights and non-trainable weights. All of these weights that I'm showing, so the 12 plus 3 weights of this simple input-output map will be trained. So if you do a training, okay, all of these parameters will be changed based on the optimization that you do. Okay, and by the way, most of the layers that we use have actually trainable weights, except for the batch normalization. We didn't go to the details of the batch normalization, so don't need to worry about this. But if you ever have a batch normalization layer, and you see here that actually it will have some trainable weights and some non-trainable weights. The non-trainable weights means that if you run the optimization, they will always be what? Fixed. So it's like fixed constants, right? So they're like constants of the network.
Like the dropout.
The dropout, I don't think, when we build something, when you do the model.summary, actually it will give you the total number of weights, and then you can check actually the total number of trainable weights and the total number of untrainable weights. So you can always check when you add a dropout later what happens. You can play around with it. Okay. So now this is the weights attributes of a layer. Another thing that a layer has as an object is actually the trainable Boolean. This is the most important one. This is the most one related to today. So this Boolean you can set either to true or false. If you set it to true, what happens? All of these weights become what? Trainable. False, they become non-trainable. So if we're using the transfer learning and we get a model from someone else, the first thing we have to do is what? freeze the layers by setting the trainable attribute to be false. Okay, this is an example again. So all of this is just examples. Okay, just to demonstrate the idea, and then we build the network, and then we start training. So we built a very simple network that has 3 inputs and 3 outputs. Very simple. And what I show you here, so this is a 3x3 matrix of the weights before training, and this is the 3x3 matrix after training. And what we did in this very simple example is that we set the first layer to be trainable and the second one to be non-trainable. Sorry, we did the other way around. I think the layer 1, okay, yeah, exactly. We set the layer 1 to be false. So layer 1 has fixed constants. The layer 2 is the one that we learn. So you see here, I print layer 1 before learning and after learning, and what happens? Exactly the same. They don't change. But if you look at layer 2 before learning and after learning, you're going to see that the parameters change. So this is, I'm not training the output layer, I'm training the weights that's connecting. So here, this is a 3-layer input and hidden layer and output layer. Each of them has 3. Okay, so that's why you have in the end 12 parameters, 3x3 matrix and a 3x1 vector. This is just an illustration that this is really what's happening inside of the code. And this also shows you how can you access all of this stuff. So for example, this is one very important thing. How do you get the weights? How to see the weights of each layer so that you see what's going on. This is very powerful, okay? So that when you're debugging the code, so what we did last time is that we see whether it's classifying or not, but we didn't look into the inside of the networks. This is how you do it. Okay? You look really at the network.
They have been trained, like, that's why we have the weights and we can love and
Even if you don't have, okay, that's a good point. So these layers even if they're trained or not trained, the weights, you initialize them randomly. So here they were initialized, you see, completely randomly, and the bias was 0. Okay, the same. Let's take the second layer, because the second layer was actually learned. So that you see, this was a random initialization of the gains, and a 0 bias. And by the end of the training, the bias was not 0, and the weight matrix changed here. Okay, so you always have to initialize. What happens if you initialize this to be 0? What happens?
you mean the weights or
The weights. It's a very, very bad approximation. It's a very bad guess, right? It will take exactly very long time to start from the origin of this huge parameter space and jump to really to somewhere where it has a value, because you know for sure that the map from the input to the output is not 0, right? Because if the weights are 0 and the bias is 0, the output is 0, right? So it's a very bad way to initialize to be 0. Okay.
So here you start training the model or it's already
What I'm showing here is just the Keras API. So just the commands in Keras, and we haven't done any transfer learning yet. I'm just showing 3 things that you need to get out of this. This idea of the trainable attribute of a layer, the weights attribute of layer, and how can you get them, okay? And the idea of trainable and non-trainable. This is it. Very simple. Yes. Yeah, of course. By the way, this is how you get the model. When you download the model, what do you download? You just download the model parameters, the number of the weights. Okay. How big is it? You can always check. This is something that we had in the last time. You can always check it actually. As a program, as something that you put on the hard disk, this is the size of this very small network that we have. It's 96 bytes. If you look at what we did last time, actually it was in the range of, I think, of megabytes or something like that. Okay, what we did for the CNN last time. The first tutorial, it was a range of kilobytes. So you can download it. It's just like a file. Very simple. You can save it. The model of today will be huge. So we're going to see how large it is. Okay. Yes. No, it has the bias also. See? It's 12 because this is a 9 by 9 matrix. So the input is 3 and the output is 3. 3 by 3 plus 3. It's not the first one. Okay. Yes, that's right.
And also the weight.
There are 2 layers.
No, the value of the weight.
The value of the weight.
Yes.
Are they from 0 to 1? That's a good point. I think so. I think it's normal. I think it's not allowing more than that. Why would you? That's a good point. I didn't think so. I think you can choose to have the larger weights, but in general, you don't need that, right? Because from 0 to 1, you can have the whole range. Right? I don't know. That's a good point. Maybe you can look at it. Now, this is another illustration. So again, this is, if you go through this, reading this part at your pace at home, inshallah, you're going to find this is explaining really this idea of the freezing and the unfreezing and the fine tuning and all. These are one caution. Be careful that this is not a code to run. This is only explaining the code. Okay, but don't run it. The running part starts from here. Okay, from this part. So now we're gonna do a fine-tuning image classification on a cats versus dog dataset. So we're interested only in cats versus dogs, and we're gonna be using the ImageNet dataset. Okay. Let's see. Let's download it. I hope this doesn't take a long. Yeah. Okay. So you see that the ImageNet dataset is 700 megabytes. So now we're really talking about, because you remember this was a dataset of 1,000 classes, and I think it had about 25,000 images in total. I think. Okay. And we're gonna this is gonna take a while to download, and after it does, let's just plot the first 9 images, and you're going to see something very interesting in this data set when it prints. And one thing to show you here, that actually the data set of ImageNet is huge, okay? But what we're only downloading is it's a sub data set of it, which is the cats versus dogs. So the TFDS is a library. It's one of the libraries included in TensorFlow. It's called TensorFlow dataset. You can use it to download like available datasets that are in the internet, and you can specify if you're not interested in the whole dataset, the dataset itself can sometimes include subparts of it. So, for example, if you're interested only in cats versus dogs, ships versus cars, and so on, something like that. So this is also allowed, and this is the way to do it. What we're going to do is that we're going to be using, so the data set that we have is only 93,000 images. So this is the data set we're going to train on. If you're building a neural network from scratch and you want to learn on this is too few data. So this is considered really not enough to train a neural network. If you remember, for the MNIST and for the CIE483, we had like 60,000 images. So this is a lot of images. Less than 10,000 is considered to be very few.
From ImageNet, you take only the
cats and dogs, exactly, and we took a part of it, exactly. We split the data set. We split into 40% of them will be training, 10% will be for validation, and 10% will be the testing. If you remember from last time, okay, whoever was awake from last time, we had the one way of doing the regularization is to not only have a training data set and a testing data set, is to also use a validation data set that's used within the training process to check every number of epochs whether you're doing good or not, before waiting till the end of the epochs and the end of the training to see the test with the test data set. So the validation part is used also to tune some hyperparameters during the training. So this is a very nice way. It's not using for the training itself, but used to tune the hyperparameters on the go.
So when you use the validation picture or validation image, use it without the label, right?
Use it also with the label. Use it also with the label to tune the hyperparameters. So use them for the tuning of the hyperparameters, not for training of the weights. Okay. So this is the idea of the validation data. And so it's a very powerful way to do it. Okay. And you see, this is the number of validation samples and the number of test samples. And these are some of the images of dogs within the data set. Okay. What is your first observation?
High quality.
More quality, yes, from last time. What? Size, exactly. They have different sizes. They're not all normalized. This is what makes ImageNet a little bit complicated. Okay. So they come with different sizes, and it's up to you. Do you want to train the data on the unsized images? Do you want to resize them and rescale them? This is what we're going to do. We're going to rescale them and resize them.
So the features are different.
The abstract features, they are the same. So the network learns the same features for both. And when you do the classification, you give different weights. So you take, I don't know if you have 1,000 features that you learned in the last flatten step, you can start giving weights to these images. So this picture of a cat will have 0.1 from this feature, 0.2 from this feature, 0.0001 from this feature, and you sum them. What's happening, you don't know, but this is the mathematics of what's going on. Features, the abstract features, of course. The network will learn these features, exactly. Okay.
There is other way to have multiple size because you have to specify the number.
For us, in order for the data set, they give it to you general, you do with what you want. This is the idea. As a programmer, you do what you want to fit it to your neural network. The neural networks that we're going to using, they always have the same input layer. So you always have the same size, which is exactly what we're going to do. Okay. This is one fancy way of using Keras to do the resizing. Okay. So again, look at these parameters in your own pace. We did, again, something to keep in mind. In the different tutorials, we do different operations we do the same operation in different ways so that you learn different techniques of doing the same way. Okay. This is, again, data augmentation. So we're going to do some data augmentation layers. We're going to do random flips and random rotations. And this time we're going to actually take a look on what's going on of this data augmentation. But first, something that we can do here with TensorFlow is that we can ourselves do the batching of the data sets. Okay, so by using methods inside of, or these functions inside of TensorFlow, you can batch the data set. Okay, so you can make them in batches. So all of this is data pre-processing, and you can print how many batches do we have. You can see that now we're going to have, we started with 9,000 images, and we said we want each batch to have 64 images. So if you divide the 9,000 by 64, you're going to get some 145 something. We did it, but we did it last time. It's done included in Keras. So when you do the Keras and you set the batch size and you give it as a parameter during the model compiling and the model fitting, it does it for you. This is one way that you can do it outside, so that you have more controls. Again, same way, same operation, we're doing in different ways, so that you learn different techniques of doing the same thing. Exactly, outside of the layer. Exactly. And then this is one example of the image. Again, we're going to look at one image and the different ways that it can be that you can have data augmentation. So just for visualization. So again, so if the picture of the dog, maybe for example, was this one, maybe probably this is the original one. This is what data augmentation does. Okay. Again, not all of these images will go into the training. Remember, it will be random. One of them, okay, will go into the training data set at one epoch. The next epoch, another image of it will go. Okay, another variation of it. Let's put it. Now, this is the interesting part. Keras, by the way, has also some predetermined models that you can immediately download. Okay, so it does it for you. So it gives you. You can either look on the internet for the models and how to download them. And again, remember, there'll be just gonna be like megabytes or maybe larger from the megabytes files that you download. This is the network, and you can look at the weight. With Keras, it already includes the exception. Exception is one of the trained networks done by Google. Okay, we're going to see how large is it in a minute. We set the image, the input shape to be 150 by 3 by 3 RGB layer. Okay, and then we say this is one way that's again, it's the API given by Keras. We said that we don't want to include the top layer. What does the top layer here mean? What is the top layer that we don't want to include here to do transfer learn? No, the top layer. The classification one. No, not the features. The features are not the top, the one on the bottom. Again, remember, top and bottom is with respect to the user. So the user sees the classification layer to be the one on the top. Okay. But with respect to the image, the first layers it will go through are the ones for the convolution. And at the end, they will see the what? They will see the classification. So here, by include the top, it means the top layer that's responsible for the classification. Okay. Let's run this one because I think it will take some time. What we're gonna do here is, let's see. We're gonna, what does this line do? Freeze what? The convolution part, exactly. The feature extraction part. Okay. And then we're going to create, again, our new model on top of that. So our new model will be simply an input layer that takes the images, so 150 by 150 by 3. And we're going to add on top of that, okay, actually, it's better to look at it here. So this is the input layer. We're going to do the rescaling inside of the neural network. So this is one way you can do it. So remember last times we were doing the rescaling outside. Here we're going to be doing the rescale to be the first layer inside of the network, just some operation. That's why you see it doesn't have any parameters. It's just some operation that you do. And then we're going to use the exception based layer. How large is it? 20 million parameters. Okay, almost 21 million parameters. Okay, and because we set it to be false, what is this n? It's not trainable. Exactly, it's not trainable. So this is trainable, and it says no, it's not trainable. And you see that this is the last layer. And remember, this is only the output layer. So the output layer is 5 by 5 images. So it has images, it has features of 5 by 5, and there are 2,000 of them, 2,048 features. Each feature is 5 by 5 image. Exactly. This is the output of the feature extraction before the classification. The first thing we're going to do is that we have all of these images, these small features. We need to decide what we're going to do with them. The first thing we're going to do is that we're going to take an average of these images. Okay, we're going to convert these images into just one number. So the 5 by 5 by 2048 will be converted to 2048 by 1. Okay, we're going to add some dropout for regularization, and then we're going to connect it in the end to one output layer. This output layer has only one neuron that's either 0 or 1. 0 means cat, 1 means dog, or vice versa, depending on what. We don't want the probability. You just want to know it's cat or dog. Again, you can play around with it and change it. But we are using average pooling. If you remember, the last time we talked about the max pooling. From each picture, we take just one number. Okay, we take the average of the whole picture, of the whole feature, and give it one number, an average. Okay. So in the end, this network has a total of about 20 million bytes, which is in the 20 million parameters, sorry, which will count to 80 megabytes of a file of size on the hard disk. We're going to only train 8 kilo of them. And we're going to use the rest from exception. Okay, let's see. Let's. The 8 kilobytes are only the last layer, the last layer that we added here. So you see, remember, we had only one connected layer. We have only weights from 2048 to 1. So if you imagine we have 2048, you connect them only to one output.
We don't have
This is the classification from 2048 to 1.
What's the hidden layer?
No hidden layer. The hidden layer is the 2048, let's put it this way. But it has been learned through the convolutions. So instead of having input, hidden layer, output, which is 1, the input goes through convolutions. You get the hidden layer, which is 2048, and then you point them, you make them into a funnel, go to one value. This is the size of that. What? Exactly. This is the flattening part. Exactly. This is similar to the flattening. Exactly. So what you did here with the average pooling is simply similar to flattening. Okay. Let's compile. How well do you think this will work? Good, inshallah. Okay. Let's see. Remember, we're going to only do 2 epochs on 2,000 parameters. Okay. And the data set that we're using, by the way, we're doing a little bit of a trick here. We're using the data set, the same data set that was trained on ImageNet. Okay, so this is the trick. We're not using on a new data set, but we're using only part of the data set of ImageNet. Okay, so this is what we consider to be our data set that we came up with. But if you want to train this on different data set, try it. Different cats and dogs that were not included in the ImageNet. Try it and see what happens. Okay, so immediately we've already reached 80% of the classification. We're still in the first epoch.
We take the whole data set from ImageNet.
If you take the what?
Whole data set from ImageNet. Because previously take only the picture of
Yes.
So we take the whole image, the whole data set to be same.
Remember, we have 2 things here. We have the network that was trained on the 1,000 classes. So this exception network was trained on the actual ImageNet dataset, and it produces 1,000 classes. Okay, so its last neural network part, its class classification produces 1,000. Okay, probabilities. What we did is that we removed the stop layer, we used the feature extraction part, and we connected it to our own network, our own fully connected network, and we had the data set that we're training on, we borrowed it from the ImageNet. Okay? We could have borrowed it from somewhere else, we could have tried it from somewhere else and see what happens, but it would have probably taken longer, especially when we're doing the fine-tuning it. But again, it's something you can do. You can try it on a different data set of cats and dogs. We did a little bit trick of the data augmentation, remember? So that at least we have a different network from the one on ImageNet, because ImageNet doesn't have data augmentation. The data augmentation means that we're not kind of having the same data set of ImageNet, or at least borrowing part of it. We made our own new data set by playing around with the ones that were in ImageNet of the cats and the dogs.
So we are sending the top layer on image that were in the original set of new.
That augmented, randomly data augmented data set.
But it's
Similar. Yes, it's a word. Again, remember, this is a class, right? We're not interested in staying here for a week trying to train this. Okay, but again, feel free to play around with it. Again, you have the base code, your sky's limit. Okay. Now, okay, what we're gonna do now, we finished by the way, we finished the training, and the accuracy was 94%. That's it. Very quick. We finished the training, and you have a 20 million parameter network ready for you, able to classify cats and dogs with this accuracy. Okay, that was it. This is transfer learning. Let's do one last step of fine tuning. Okay, remember the fine tuning is doing what? What we're gonna do now is doing the base model. We're gonna make it trainable again. What does this mean? We're gonna unfreeze all of the parameters, but we have to make sure that we use a very low learning rate. This is what we do here. Okay, we're using a 0.0001, 0.0401.
So the whole 20 million will be trained.
The whole 20 million will be trainable. So if you print actually it's now printing, it's now doing the training, but you see here, this is the number of trainable parameters. Okay, so you're training the 20 million ones of the feature extraction very slowly, again, playing around with it a little bit. And you're also training the classification a little bit also. So this is the fine-tuning stage. We're not really training from scratch. We already are available in the parameter space. So this is a 21 million parameter space. We're already very near the optimal point, but we're just moving it a little bit. We don't want to make large jumps. Just move a little bit. It's like moving in the neighborhood and see if you find something better or not. This is precisely what the fine-tuning is.
What's the best fine-tuning if we have that identification?
Very good. Let's see. We're almost there. So this is the accuracy of the training now after doing the fine-tuning. And by the way, we're going to do only one epoch. So we're just one epoch and see how well will it reach. We reach a binary training accuracy of 85%. Good or bad? Good or bad? It's less than the previous. Yeah, the last training we did was 94, but now we have 85.
It's good.
Exactly. Never decide if it's good or not, except when you test it.
But better regarding the number of the data, consider it good.
The number of data points, you mean?
Yes.
The 9,000.
No, I mean the whole.
For 21 million parameters?
All this for training.
Now we're training 21 million parameters. In this step, we're training 21 million parameters. Almost 21 million. It's huge. What?
Should be improved, not
So this is what happens. The test accuracy is boosted now to 95%. So you see? So the fine-tuning did work. Okay, something that we didn't do, actually, we didn't do something for you to test at home. Try to evaluate the model after this step. So before the fine-tuning and see what happens. Something actually it was not done here. Okay, maybe I'll add it and see what happens. Okay, but again, this is the purpose of this tutorial is really to show you the workflow of doing the transfer learning. So whether the fine-tuning will work or not is up to you. Okay, maybe you make things work, maybe things will get better. But again, it's something that you add on in the end. If you're not satisfied with the fine tuning, go back and you already have the parameter. You already finished the training. You have the accuracy. Something very important is that after doing these stages, if you're in the project, for example, and you have something similar to this, you can always save the parameters. So before moving on and training them and changing the network, you can always save this model to a file, and this is what we did. We downloaded the file from outside. Okay, so this was transfer learning. Very simple idea, but very powerful. Okay, any questions? No? Okay, so let's stop sharing.